The third talk in our four-part series on renal homeostasis will focus on acid-base homeostasis. Again, we will come back to this case at the end of the talk, just to see if we can tie things in to acid-base homeostasis. This reminds us of our definition of homeostasis and the homeostatic functions of the kidney. As we said, this talk focuses on acid-base balance. Okay, so here's a 45-year-old male psychiatric patient who presents with lethargy, mild dehydration and vomiting. He has a metabolic acidosis with hypokalemia and a urinary pH of more than 6. We're going to think about the pathology here, the role of the kidney in acid-base balance, and what the impact of acid-base homeostasis might be on other electrolytes. So just very briefly, if we look at this patient, he has a metabolic acidosis, but unusually for metabolic acidosis, he's hypokalemic, and his urinary pH is not very low. If his kidney were working normally, the metabolic acidosis should stimulate a loss of hydrogen ions in the urine, and his pH should be low. He should be losing acid in the urine. This is not the case here. So this is a case of renal tubular acidosis, which presents like this, with hypokalemia, metabolic acidosis, and an inappropriately high urinary pH. When we're thinking about acid-base homeostasis and the kidney, we just need to remind ourselves of the broader picture of acid-base homeostasis. And the first thing to remember is that hydrogen ions are a normal byproduct of many metabolic activities in the body, particularly those that use energy. Therefore, one of the roles of the body is to get rid of that excess hydrogen ion. And there are two systems for doing this. The first is, and the quicker one, is the loss of CO2 through the lungs. So there's the respiratory component of acid-base balance. And then the second is the maintenance of bicarbonate and loss of hydrogen ions in the kidney. So that is the metabolic or renal component of acid-base homeostasis. Today we're going to focus on the renal component. So when we're thinking about how the kidney deals with excess metabolic acid or hydrogen ions, there are three main ways in which this is done. Firstly, bicarbonate is reabsorbed through the activities of carbonic anhydrase in the proximal tubule and to a lesser extent in the distal tubule. Proximal tubular reabsorption of bicarbonate actually accounts for 70 to 80% of all bicarbonate reabsorption in the kidney, but it does not really play a part in fine-tuning of hydrogen ion loss or control of acid-base balance. The bit that really varies with acid-base balance is hydrogen ion secretion in the thick ascending limb of the loop of Henle, the distal tubule, and the collecting ducts. And this is very dependent on acidemia and the acid load in the distal tubule. This is where the fine-tuning of hydrogen ion secretion takes place. And when we think about the distal tubule, we'll see that because this is where the fine-tuning takes place, there is a lot of other electrolytes may be affected by this. Finally, it's worth remembering that in the kidneys, the loss of large amount, a large amount of hydrogen ions, could potentially make the urine so acidotic as to be damaging to the urinary tract. Therefore, the hydrogen ions in the tubular fluid and ultimately in the urine has to be buffered. And there are two buffering systems that deal with this. One is the phosphate buffer and the other is the ammonia buffer. The phosphate buffer is due to the secretion of phosphate into the renal tubules, which then binds with the hydrogen ions to form the weak acid, phosphoric acid. Similarly, ammonium, NH3, binds with hydrogen ions to form ammonia, NH4, which is also a weak acid. How does acid-base balance affect other electrolytes? Well, if we think back on the last two talks, we will soon realize that pH affects calcium excretion. It increases the excretion of calcium and magnesium. What we just talked about in terms of the phosphate buffer means that a high acid load in the urine will actually increase the loss of phosphate in the urine as well, leading to hypophosphatemia. And as we know, extracellular potassium concentration can be profoundly affected by acidemia. Most of this is due to the shift of potassium from the intracellular to the extracellular space in acidemia. However, the reverse happens in the kidneys. In the kidneys, when there's a high acid load and acidemia, the competition for sodium exchange in a distal tubule mean that hydrogen ions are exchanged in preference to potassium ions. I said it's not really a converse thing, it's the same thing. So therefore less potassium is excreted in the kidneys in acidemia, which also reduces the loss of potassium and potentially increases extracellular potassium concentration. Now there's a flip side to that, which is in long term, acidemia leads to a overall loss of potassium from the body, simply because acidemia leads to a larger amount of potassium in the extracellular fluid, and therefore over time more potassium is lost in the urine. And although we might have hyperkalemia, we have a reduction in total body potassium. And this is exacerbated by the fact that potassium is that acidosis or acidemia stimulates the aldosterone, the renin-angiotensin aldosterone system, increases the secretion of aldosterone, and that of course promotes potassium loss. So if we look at our diabetic patient who looks ketoacidotic to me, clearly the metabolic acidosis, if the kidneys are working properly, should lead to an increase in in hydrogen ion loss in the kidneys, particularly through the regulation of hydrogen ion reabsorption in the distal tubule, and a decrease in reabsorption and an increase in loss of potassium. As we described earlier, that would be at the expense of magnesium and phosphate, and calcium as well, but the big ones are magnesium and phosphate. And also, because of the effects of a lack of insulin in this case, and an increase in the counter-regulatory hormones, there's also a loss of potassium. So although the potassium concentration in the extracellular fluid is high in these patients, the total body potassium tends to be low. If you have any questions, you can bring them up in class. In this talk, we focused on acid-base balance. In the final talk in this series, we will look at glucose homeostasis and the kidney. Thank you.